Okay, so look here, guys. As I explained last time, resistor can connect it in series this way. So, here, for example, I have here R1, I have here R2, also I have R3. They are connected in series this way. Okay. And if I do that, if I connect it in series this way, and the voltage here, I'm going to assume the voltage here is V, and positive here, negative here. This is the voltage drop on the three resistors. So, as I told you before, because they are connected in series, so actually this voltage is distributed on them. So here, if you have here positive, negative V1, positive, negative V2, positive, negative V3. So V should actually equal V1 plus V2, V3. So the voltage drop is distributed on them. Okay, this is if they are connected in series. But they have the same current. So we don't distribute the current. It's the same current, but the voltage drop is distributed on the resistors. Is that okay? I told you in this case, I can say this circuit is equivalent to R equivalent, and we have here V, and we have here I. So the same I. So the same I here is gonna go through R equivalent. And actually R equivalent is actually R1 plus R2 plus R3. That's what I said last time, okay? So in this case, I can say I equal V divided by R equivalent. So the current, I can get the current this way, okay? And then, if you know I, you can easily get V1, because V1 is actually using Ohm's law. V1 is actually I times R1. V2 is actually I times R2. V3 is actually I times R3. And if you add them together, you will get V. That's for sure. If you add them together. Okay. Any questions? Also, I give you a formula, quick formula. You can use it. Okay. The quick formula is VI equal, I here can be 1 or 2 or 3. VI is equal to RI, okay, divided by R1 plus R2 plus R3, okay, times V. So this can give you the ratio of V, because I told you V is distributed on them. Okay, so you can tell now, the higher the R, the greater the voltage RI. You can have said, so if I connect the three resistors, one resistor is much bigger than another one. So you will see most of the voltage is going to be on this one, and the other one is going to be very little, very small ratio. You understand what I'm saying? This is the case in voltage. When I talk about the current, the story will be different. Okay? So now, if you have big resistance, for example, 10K, and then here we have 1 ohm, we have here 2 ohms. And I put here, for example, 20 volt. Okay? I will leave the calculation to you. You can use the formula I have here to do the calculation, but you will notice if you calculate V1, V2 per 3, you will find here this one will take maybe 90% or more than 90. So this one will be 19 something. So it's going to be very close to 20. Here, very small voltage, because the higher the resistor, the higher the voltage of this resistor. Okay? It can be divided equally. For example, if you have here 5K, and you have here another 5K, and here you have 20 volt. Because they are equal, so this 20 volt is going to be divided equally. So this one takes 10, and this one takes 10. Okay? But again, you can see the formula we have here. Any questions? That's what I explained last time. Okay? This is for voltage for series resistors. Now I'm going to talk about parallel resistors. Okay? In case of parallel resistors, so they have a resistance this way. We have another resistance this way. I have, for example, another resistor this way. I'm going to call it R1, R2, R3. They have to have the same node here. They should have the same node here. If you call it parallel, they have to have the same node here and the same node here. Okay. and then I can have a current source this way. We're gonna call it I. So what happens is the current I is gonna come here, and this I is gonna split. So we have here I1, here we have I2, here we have I3. And they are gonna be added together again and come here. So that means I should equal to I1 plus I2 plus I3. Yes, but it's gonna split. Okay? One more thing, so the current here is gonna split, divide, but the voltage is the same. So V1, so the voltage here across R1, V1 equal V2 equal V3. They have the same voltage as long as, because I told you before, this is one node. All of this one node. So the voltage here is similar to the same voltage. Same thing, this one node. So they have the same voltage, but the current is gonna be divided. Okay? And now, the very easy, and I told you also, this one, this circuit here is just equivalent to, here I have R equivalent, and then I have here the current I, and the R equivalent. And the formula for R equivalent is 1 over R equivalent equal 1 over R1 plus 1 over R2 plus 1 over R3. Okay? So you need to do the addition, and then you need to flip it to get R equivalent. Okay? And then the voltage here V, okay, which is actually the same voltage here, the same voltage here, the same voltage here, the same voltage. So the voltage actually is I times R equivalent. Okay, this is the voltage. Okay. Now, so I1, how can you calculate I1? Using Ohm's law. So I1 is actually V1 divided by R1. Okay, and actually, so V1 here is the same like V because they are in parallel. So should equal R equivalent divided by R1. Okay. Same thing, I2 should equal R equivalent divided by R2 and so on. Okay. So I give you one case, which may be the easy case or straightforward case when you have only 2 resistors. So when I have only 2 resistors, for example, here R1 and R2, and then the current here is I. So I is coming this way. So it's going to be divided here I1 and I2. So if I use the same formula I explained here, so you can see here I1 equal to the other resistors, which is R2, not R1, R2 divided by R1 plus R2 times I. So this is the ratio I1 will take. What about I2? I2 should equal, here I calculate the current I2 in the resistor R2. So it's going to be the other resistor, which is R1 divided by R1 plus R2 times I. Okay? It's very obvious if you add I1 plus I2, I1 plus I2, you equal to I. So the math can work this way. Okay? So now let's look at the interesting part or the important part you should realize, understand. So based on what I explained here, which branch is gonna take bigger current or which higher ratio. Okay, so you can tell here if the resistance, if the smaller resistance, okay, is gonna take more current than, so here if I think something is wrong here, right? No, I think that's correct, right? So here I1 equal R2 divided by R1 plus R2. Okay, I think that's what I explained last time. But the thing here is that if you have here current I, okay, so here you have resistance R1, you have resistance R2. Okay, if R2 is a smaller resistance, for example, this one 1 ohm, and this one, for example, 10K, for example, you will find most of the current is going to go through the smaller one. Okay, you can tell. So is that the math here is going to work this way? Yes, because if you look at this I, I'm going to call it I2. Okay, so I2 equals the other resistor, which is the big one. So 10K divided by 10K plus 1 ohm. Okay, so the ratio will be big. Okay, So this is the most important thing you should understand. If you have two resistors connected in parallel this way, so what happens very simple. If the two resistors are equal, if R1 equal to R2, if the two resistors are equal, current is going to be divided equally. Okay, so this one is 10 ampere, so this one 5 ampere, and this one is 5 ampere. Okay, otherwise, the smaller resistance is going to take bigger share of the other one. Is that okay? That is why, and that's what we are going to do this course, by the way. Okay, that's why if you have like a big resistance, like for example 10 mega, this is a big one, 10 mega ohm, and then you have here something like 1 ohm. 1 ohm is almost short circuit. Okay, so actually you are gonna find all the current, 99% of the current is gonna go there, and almost there is nothing is here, almost nothing. Okay. That's why in this course and somewhere in this course, if you have a short circuit this way, so the short circuit like a zero resistance, you have zero resistance. So all the current is going to go this way. So this one, for example, 10 ampere. So everything 10 ampere will come here and zero is going to go there. Okay, using the same concept. So again, here is different from what I explained here in case of series resistance. Here, the higher the resistance, the more voltage is going to take out of the total voltage. Here, the smaller the resistance, the more current is going to take from the total current. Okay, any questions? Okay, so yeah, sure.
So the equations we're talking about for the resistors in parallel, what if there's more than two? What do you put in the numerator?
Yeah, so if it is more than 2, you want to get the formula for this one, okay? So for example, here I have R1, I have R2, I have R3. We don't have like an easy formula like the series one, but still you can do something, okay? For example, this is a very good question. So for example, I have here I, the total I here, okay? I wanna get the current here, for example, I3, for example, okay? So in this case, I have two options. One option, I can replace these two resistors with equivalent resistance. So it becomes like we have here R1 parallel with R2, okay? And then we have here R3, okay? And we have here I. And in this case, I can use the formula that for two resistors, we have easy formula I can use, okay? So here, I can say here I3 is equal to I multiplied with the other resistors, which is R1 parallel R2 divided by R1 parallel with R2 plus R3. And you know R1 parallel with R2 is actually R1 times R2 divided by R1 plus R2. This is one way. You may not like it, but there's another way I'm going to explain. Okay? The other way, is this okay? The other way also is if you have here R1, R2, and R3. Okay? And we have here R. Okay, so I can say this one is equal to the same, like here we have R equivalent, or okay, and then we have here R. Okay. And in this case, 1 over R equivalent equal 1 over R1 plus 1 over R2 plus 1 over R3. So you can, given R1, R2, R3, you can calculate R equivalent. And then the reason I calculated R equivalent because I can get V. I can get V here. V equal I times R equivalent. Okay? And now, this V is the same voltage here because they are in parallel. So is this equal to V1, V2, V3? So the voltage drop, so here V is the same like V1, V2, V3. Okay? Once you get V, I can get all resistors using Ohm's law. So once I know this voltage here, I just divide by R1, I get I1. I divide by R2, I get I2, and then divide by this one, I get R3. Any questions? Okay, thanks. Good. So Okay. So last time I explained this example, but it was at the end of the course lecture. So it was quickly. So I'm gonna repeat it again. So as you see here, guys, I give you this circuit, and then I ask you calculate the equivalent resistance assumed by the source. So what is the equivalent resistance here? Okay. So try to see. The most difficult part, in my opinion, is you need to know which resistors are in parallel and which resistors are in series. Okay, that's the most important thing. So as you see here, this current is gonna come this way here, and then this current is gonna split between these two resistors, and then it's gonna be collected here. So this current IS is gonna be here, like here, IS here. Okay. If you add I1 plus I2, give you IS, because it's gonna split, and then add it together here. Okay. And then the same current IS here is gonna split again. So I3 plus I4 plus I5 equal IS. And then the current is gonna be added together again and come here. Because make it easy. Current is a charge. The charges are not gonna vanish. It's not gonna go anywhere. Okay? They just split. So some charges go here, some charges go in, but at the end, you are gonna get the same number of charges coming here will be the same number of charges here. Is that okay? So again, it's very obvious that R1 and the R2 are parallel. It's very obvious. Why? Because they share, when the current comes, the current is split, but they have the same voltage. This node is the same node like this one. Voltage here is similar to the voltage here, and the current is split. So that's why I can get this resistance equivalent to this resistance, okay? Using the formula I explained. That's what I did here. So here is the equivalent to this part here is equivalent to this RP1, which is R1 times R2 divided by R1 plus R2. Okay, I calculated it, using this number given to me, it was this amount of ohms. Okay, now look at these three resistors. Again, these three resistors are in parallel. Why? Because they have the same voltage, all of this one node, 1 point, and the current is going to split between them or divided between them. So that's why this resistor is equivalent to one resistance here. Okay, and I can calculate this way. Okay, which is 1 over R equivalent equal 1 over R3 plus 1 over plus 1 over. Okay, so you can, if you just do the math, it will be something like that. You can calculate it. Okay, now given IS, so here I give you IS. Okay. What do you want? So I want to get I1, I2, I3, I4, I5. Okay. So let me ask you a question, and this is the easy part. Let me ask you a question. If I can know the voltage here, V1 should equal to V2, the same voltage. So if I can calculate the voltage here, it's gonna become very easy to calculate I1 and I2. Very easy, right? Same thing here. If I give the voltage here, because the voltage V3 equal to V4, V5. If I can give the voltage here, I can simply calculate the current here using Ohm's law. Okay. So now the question is that, look here. So the current is gonna come this way. Okay. But let me, because I think I jumped to the second one before I finish the first one. We didn't finish the first one yet. So the first one, I want to see the total resistance. So now this is the resistance for this part. This is the resistance equivalent resistance to this part. Okay. What do you mean by equivalent resistance? What this means? It means when I put this resistance, nothing will change in the circuit. So it's the same current. The same current will flow, and also the voltage here will be the same like the voltage here. Voltage here will be the same like the voltage. Anyway, so now you can see these two resistors are in parallel. These three are in parallel. But this one and this one are series. Why? Because the current is the same current. The same current is going to flow this way. So now I can get the final resistance, which is equal this resistance plus this resistance, because these two are in series. Okay. You can even notice here this spring, this resistor and this resistor are in series, because the same current is going to flow through these two resistors. It's the same current is going to flow here. Anyway, so by this way, I was able to calculate the total resistor, which is 7/3 ohms. Okay. Now let's come to the second question. The second question is, What if I want to get the voltage here, and also I want to get the current here and here, okay? So again, this is the most important thing. Look here, guys. Again, the easiest thing here to do, if I use a voltage, okay, so it's easy because the voltage here is similar to the voltage here. So when I divide the voltage by R1, I get I1. If I divide the voltage by R2, I get I2. Simply because they are in parallel, they have the same voltage. Same thing here. If I know the voltage here, I can easily calculate the current here. The current here is the current here. Is that okay? So this is it. Again, there are different ways, but this is a very easy way, a very straightforward way. So now the question is, how can you get the voltage here? How can you get it? Okay, because this equivalent resistance, I times the equivalent resistance will give you the same voltage here, give you the same voltage. Okay. So all what I already got RB1. So RB1 here is 4 divided by 3 ohms. Okay. If I multiply and it's the same current here. Okay. So if I multiply I, which is given to me by 12, if I multiply 12 times RB1, I get the voltage drop. Same thing. How can I get the voltage drop here? Okay. The voltage drop here is actually I, because it's IS, which is the same current. Okay. So IS times RB2. Okay. And I already calculated RB2. So again, once you have the voltage here, I can just divide it by R1 to get the current here, divided by R2 to get the current here. Once I get the voltage here, so I'm going to divide it by R3 to get I3, divided by R4 to get I4, divided the voltage by R5 to get I5. That's it. Okay. So let me ask you a question. What is VS? What if I want to calculate VS? The voltage here on this current source. What is the voltage here? Okay. So again, the voltage here is actually the voltage between point A and C, because this is point A and this is point C. It's the same point. It's the same point. There is no resistance here. It's the same point. Okay. So if I can, and you can see this one is in parallel with this two. Okay. So the voltage here, the voltage across this current source is equal to the voltage here across this one. Okay. And it's very obvious. These are in series. So if I want to get the voltage between A and C, so I need to get the voltage here plus the voltage here. Got what I'm saying? So now I already got the voltage here. I think let me see here. Okay. So yeah, so here I did it in different way, but you can do it in different ways. So one way to put the voltage from A to C, I just multiplied I times R equivalent. It was 28. Okay. So it's another way. Another way, as I told you, you can get the voltage here and then you can add the voltage here. It will give you the same result. Okay. So if you see here, this one is 16 and this one is 12. So if you add them together, 16 is the drop here. 12 is the voltage drop here. So if you add them together, you get 28. So there are different ways. Okay. Any questions? Let's see another example here. Here I wanna calculate the equivalent resistance when you look from here. Okay. Try to see here. So the current IS, this current IS, the current is gonna come here to R3, and then this current is gonna split between R1 and R2, and then IS is gonna come back here again. Okay. So it's very obvious here. R1 is in parallel to R3. Sorry, R1 and R2 are in parallel because they have the same. This point and this point are the same. The voltage also here is the same like the voltage here. So I can use the formula for the parallel resistance to calculate this resistance here, RB. So RB here is actually R1 in parallel to R2. So you can use the formula we already know it. You don't need to do this way, but you can, because in case of two resistors, it's R1 times R2 divided by R1 times plus R2. Only this is the general formula for any number. But anyway. So now I got so RP here is equivalent to these two. Okay. Again, because this may confuse the students. What do you mean by equivalent? What equivalent means? Number one, if I put this resistance, nothing will change in the circuit. Current is the same current. Voltage drop here is the same voltage drop here. That's why I'm saying it's equivalent. You got what I'm saying? It's the same voltage. Anyway, so now you see the current here is going to go through this one, and the same current is going to come here. It's very obvious that these two resistors are in series. So here I can add them together to get the total resistance. Okay. Now, if I want to calculate IS, I can use this one here. So here I added them together. I found the total resistance 10 ohms. So this one 10 ohms. Okay. Now, can you calculate IS? This IS here? Yes. It's a voltage drop because the voltage here says between A and C, it's the same voltage, right? So if the voltage here is 9, so the voltage here is 9 because this is 1 point and this is 1 point. Okay? So this is 9 and 9. So all what I'm going to do, I can divide 9 by R equivalent. R equivalent is 10. This will give you IS. Okay? So here that's what I did. So here VS is 9. If I divide it by equivalent, I got IS. Okay. Now, what else I want to find here? Okay, I want to find the voltage here. Very easy, because you have IS, right? So if I multiply IS by the resistance, I'm just applying Ohm's law. Multiply IS by R3. This gives you the voltage drop. Okay. What about now? I can use, that's what I think that's what I did here. Yeah, so here V3 equal I3 times R3 equal whatever, okay, 1.84, okay. Now, how I can get I1 and I2? Okay, you already have a formula because IS is going to be divided between I1 and I2. So you can use the formula that I can do it in 2 different ways. Okay, so here I can get this current in 2 different ways. Okay, the first way, I already know IS, which is 0.9, right? So I know the current here 0.9. Okay, if you want to get the current here, you already have a formula to do that. So I can say the current here is actually the other resistors divided by the summation times the total current. So you can use, we call it current divider formula. You can use it, okay? Yeah, I think that's what I'm doing here. So you can use current division, okay? So here I can say I1 is equal R2 divided by R1 plus R2 times IS, okay? And then once I get this current, I can subtract, I know the total is 0.9. The total is 0.9, right? So if this branch is taking 0.8, the other one should be 0.1. Because the total coming here is 0.9. This branch is taking 0.8, so the other one 0.0. It's easier. This is easier than you can apply the formula again. You can, but it's just easier to do this way. Okay? You can see this resistance R1. It took most of the current. This other one took very little current. Yeah, okay. Let's see the numbers because R1 is just 9 ohms. R2 72 ohms. So the smaller resistance is going to take more current. That's what happened here. So R1 here is only 9, the other one is 72. Okay. Because of that, I1 took 0.8 out of 0.9 because the total is 0.9. The other one took 0.1. Okay. Anyway, this is one way to do it. There is another way. I just want to show you there is another way. Look here. The voltage from here to here, okay? I know the voltage from here to here, which is VS is 9. So I have 9 voltage here, okay? This one took, what is the voltage here this one took? Okay, I think it's given, yeah, it's 1.8, okay? So here, this one here, if you apply Kirchhoff current law, here, total here, I have 9. This resistance took 1.8. So the remaining will come here, okay? Because if you take Kirchhoff voltage law, this voltage is, or you can look here is even this voltage is divided, okay? So V3 plus the voltage here. So I know the total. The total here is 9. I know 1.8, so the difference should come to here. Once you know the voltage here, okay, easy. Just divide it by R1, you get I1. Divided by R2, you get I2. Okay. I'm not wasting time. I like to solve it in different ways so that you can have the skills to learn different things. Okay, because sometimes sometimes it's a good idea to learn to do it in different ways. Okay, because Once you know how to do it in different ways, some question may need one way of these different ways. You may not have the flexibility to have different ways to solve it, okay? But you need to understand how can you do it different. Okay. Anyway, so also here, I give you this one from the textbook. I want to calculate the total. Resistance here. Okay. Let's see how it works. So look here, guys, and try to think about it. The current is gonna come here, and then the current is gonna split between this one and between this one. Okay. And then it's gonna be added together to come to here. So here, if I put this one I, so I will get I here again. This one I1 and I2 with I here. Okay. Same thing, I is gonna be split here. And then I will get I again here. Then this I is gonna split. Then I will get the same I here. Okay. So what I'm gonna do right now, just to make it easier, and this is also one of the most important things. I know you may find some difficulty about it. Sometimes if I redraw the circuit, I make it easy. Okay. So I'm gonna redraw it right now in such a way that does not change the circuit. It's the same circuit, but I'm going to redo it in a different way. It's the same circuit. Okay, so here you can see I have here EG, and then it came this way, and then I had a resistance here, 12 ohm, and then I had here this one 6, this one is EG. Okay, and then I have here 20. I have here 5, and then we have here 12. I didn't do anything. It's exactly the same thing, but I drew it in somehow a different way. Okay, and then here again, what do you mean when you say I didn't do anything? It means I didn't change any voltage, any current. So it's a voltage current everywhere. Here it's the same like this one. Okay? So here we have here 8 ohms, and then we have here 2 ohms and 6 ohms, okay? And then we have here resistor and this one, okay? Now, maybe it's much easier now, okay? So you can see here, if you want to solve this one, number one, I can take these 2 resistors in series. It's very obvious, this one, 2 in series. So I can add them together, right? So here I can get the equivalent of this one. The equivalent of this one should be one resistor here, which is 18 plus 16, which is 24. Okay? Because they are series. Okay, it's the same current. With the current here, the same current will flow here. So these 2 are in series. Now, these 2 are in parallel. Okay? You know how to calculate the equivalent of this one. Okay? So now I'm gonna call it R1. So now everything here, R1. Okay? So same thing here, it's very clear that these 2 resistors are in parallel. Okay, so you can use a formula to calculate. I'm gonna call it R2. Okay, so now the current will come this way, this way, this way. Same thing here, it's very obvious these 2 are in series. So here I can make it like one resistors, like this 2 plus 6, which is 8. This one is 8 as well. And then here, these 2 are in parallel. So I know the formula for parallel. So here I can calculate it, and then I can get here, I'm gonna call it R3. After that, the R equivalent, it's very obvious or very clear. R1 is in series to R2, is in series to 12, in series with R3, in series with 8. So I can add all of them together, and then at the very end, I have here 18, and then just one resistance here of the total resistance. Okay. Once I get the total resistance, then I can calculate the current. I can calculate the total current. Once you know the current here, the total current here, I can easily, again, the current here is the same current here. It's the same current here. It's the same current here, okay? So I can easily calculate this one and this one because you know current divider, okay? Same thing here, I can use current divider to calculate this one. Same thing, I can use current divider here because this one can be only one resistor. Any questions? Go. Okay, so here also, I just wanna, I hope you are not confused here. We can redraw the circuit. So for example, if you have a circuit like this one here, it's very clear here. I can redraw it. It's very easy. We see here, current, when the current come here, it's gonna go R1, the same current is gonna go to R2, the same current can go to R3. So it's very obvious that R1, R2, R3 are in series. So I can redraw it so that I put them in series. Okay? Because all of this is just 1 point. Okay? It's just 1 point. Look at this one here. If you see here what happens, R1, this terminal here is connected to the terminal here. Okay? If you look at this terminal here, it's connected to this terminal here, connected to this terminal here. So the 3 resistors, there is one terminal that's connected to each other for the 2 resistors. And for the second terminal are connected to each other. You got what I'm saying? So you can see here, I want to show you here, and this is very important thing. I can redraw it to make it easier, okay? But it's very clear. This point is connected to this point, is connected to this point. So this R I can connect them together. I can redraw it to connect them together. Same thing, B1, B2, and B3. So it's very obvious. This one R1 is in parallel to. Okay, let me take it here. I did print screen. Okay, I think I have to, because it's maximized. Okay, so what I'm saying, I can redo this one so that it becomes like R1 here connected to R2, connected to R3 this way. So this one exactly similar to this one, but I can redo this one. So you see here, this point E1 is the same like E2, it's the same like E3. So here I can call it A. It's the same. B1 is the same like B2, it's the same like B3. So I can call it B. Let's look at the next one here. Next one here, you can see if you have current come this way, so it's gonna one current this way and then current gonna come this way. Look at the relation between R2 and R3. They are in parallel. Why? Because this terminal is the same like this one, this terminal is the same like this one. So I can redo this one. For example, I can make it this way. We have A and B, and we have a resistor this way, R1. And then after that, I can have resistor this way, R2 and R3. Okay. I think I can do this way, but what is the relation between R1 and these two? Yeah, they are parallel. Yeah, that's true. Why? Because this is the same point here, it's the same point here, same point here is just the same point. So that means I can redraw it R1 parallel to R2, parallel to R3. Because they share all of this one node, 1 point. All of this 1 point. I can do it in different ways, but all of this just 1 point. Okay. So this one exactly. I didn't change anything. This one terminal here connected to R2 and R3. Yeah, that's what I did here. One terminal is connected to R2 and R3. Yeah, that's it here. Okay. Anyway, I think this maybe is the most difficult part, but hopefully when we do it multiple times, you can get it. The last thing we have here in this chapter is, I think I explained it before, when you model a source, like a voltage source like this one, usually we say if we have a voltage source this way and we ignore internal resistance. So this resistance I didn't add it. Okay, so as you see here, this is a circuit. I have a battery. This battery is connected to one resistor RL. But when you model the battery, actually it is like a battery here, and also we have an internal resistance here because of the material we have here. Okay, so actually this is the battery. Ideally here this resistance is zero. Ideally, this resistance is zero. In reality, practically, we have a resistor, and usually it's a small value. 1 ohm, 2 ohms, usually it's a small value. Okay? If you have a current source, it's the same thing. Ideally, the current source, it does not have a resistance here, okay? But in reality, it has a resistance, and usually this resistance is actually big resistance. So that's why most of the current is gonna go through here. Okay. So if this one, for example, 5 ampere, ideally I should get here 5 ampere. In reality, I'm not gonna get 5 ampere because there is some current here due to the internal resistance. Maybe I'm gonna get 4.9, something like that. Okay. So here I give you a numerical example here to understand the impact of the internal resistance. Okay. So here I connect the battery to a resistor 2 ohm. Okay. So this battery is going to be equivalent to ideal voltage source, 12 volt, and to also internal resistance, which is small one, 0.1 ohm, small one. Okay. All the time, that's how it is. Ideally, it's zero. You don't have a resistor. Ideally, if the voltage drop is 12, I have to get 12 here. Ideally, this is 12, I have to get 12 here. However, because of the internal resistance here, I'm not going to get 12. But it's going to be very close to 12, like something like that. After I did the calculation here, I found it is 11.43 because of the internal resistance. So when I connect here a resistance here, okay, and I assume the resistance here is 2 ohms, and then I can calculate the total current. The total current is 12 divided by the 2 resistors, summation of the 2 resistors. Okay, this is the total current here. Then I multiply this current by this resistance here. If I do that, if I multiply the current by the resistance, I'm going to get the voltage drop, which is actually 11.43. It's not 12. So I connect the battery here that's 12, but I'm not going to get here 12 because there is an internal resistance. Is that okay? I'm going to tell you something interesting. I'm going to connect it to chapter 6. Okay, what is this? This one I'm going to connect to chapter 6. Okay, so how can we avoid this problem? How can we solve it? Very simple. If this resistance is too big, the higher the resistance here, because this battery, 12 voltage is going to be divided between these 2 resistors in series. So if I can make this resistance too big, so actually it will be 12. So I can solve this problem this way. You got what I'm saying? So if I can make this resistance too big, so all the voltage drop will be here. You got what I'm saying? So that's what we are going to do in chapter 6. I'm going to connect what we call op-amp or operational amplifier. This operational amplifier has a resistance of infinity. So by this way, this one is 12, I can get 12 here. But anyway. The last thing I have here in this chapter is sometimes you have voltage sources that are in any circuit that connected in series. So we can add them together to only one voltage source. But how you are going to add them? Very simple. I'm going to tell you about the idea how it works. Okay. Look here, guys. Let me because I want to show you something. Look here, guys. So, for example, if you have a circuit and I connect to 2 voltage sources this way, look at the polarity. This is negative, positive, negative, positive. Okay. What negative positive means, as I told you before, that means the voltage here is smaller than the voltage here by VB. Okay, so let me explain this one. So if I have a battery this way, and I know this battery is 5 volt, what it means? It means if this one is X, this one has to, if the voltage here is X, the voltage here has to be X plus 5. Because that means the voltage here is greater than the voltage here by 5. Okay? Or if I know the voltage here is X, so the voltage here has to be X minus. Okay, something, I'm sorry, it's the other way. Because VA here has to be greater than VB by 5. Okay? Or the voltage drop between A and B is 5. That means if this one is X, so this one has to be X plus 5. Okay? Because that's the meaning of it. The meaning, this voltage here is greater than voltage here by 5. So this is X, this one has to be X plus 5. Or if this one is X, so this one has to be X minus 5. Is that okay? Okay. So I'm gonna apply the same thing here, guys. So if you have two batteries, these two batteries are connected series this way. Okay. So if you have here voltage X, for example, so what should be the voltage here? It has to be X plus VB, right? And what should be the voltage here? It has to be X plus VB plus VA, right? Because every time you move from the smaller to the greater, you add, right? So what is the voltage drop here between these two? Okay, so actually it should be, it's like you have only one battery, and this battery, because I connected this way, it should be VA plus VB. Okay. By the way, something like that we do it all the time. You know, when you have any device and then you connect the batteries in series, you put 4 batteries, for example. For example, I need something like I need something like 4.5 volt. Okay. So what can you do? You can connect one battery and then one battery. This is 1.5, 1.5. By this, it's like you make only one battery is 4.5. Is that okay? But the way you connect it has to be very important. So that the should be added together. So here, negative to positive. That's what I did in the first one here. So in the first one here, I added negative to positive. Okay, so I can add more. So if you have something like that in any circuit, I can simply, if you have something like that, I can simply replace it by only one source. Look at the polarity. So here this is positive and this negative, and it should be this way. Okay. What if it negative, positive, and negative, positive? As long as you connect and VA and VB. So as long as you connect the positive to the negative, you should be added together. So this one will be like it's only one source. But look here, this is negative is here, positive is here, and this one should be VA plus VB. Okay. I didn't do anything, it's the same like this one, but I just changed the polarity. I made this one negative, this one positive, okay? They are added, but the equivalent here, this one is negative, this one is positive. Anyway, hopefully I didn't confuse you. Anyway, okay? But if I connected the polarity this way, okay? Again, I think the best way to understand what I'm explaining is, as I told you, if you have a source, if you have a voltage source like this one, and this one is X, so this one has to be X, for example, plus Vs. Because this one always has to be greater by than this one by X. Okay. So let's see if I connect it this way. For example, so here this one is X. So what should be this one here? Okay. X minus VB. Is that right? Minus VB. Because the positive side has to be greater than the negative side by VB. Okay, here, from here to here, so I have to add VA. So the voltage drop here, X minus VB plus VA. Okay. So here the voltage here was X, and then here I got X. So here X plus VA minus VB. So here the voltage drop from here to here is actually VA minus VB. Anyway, I don't see any reason to connect this way, but just in case some we do circuit analysis. Same thing if you have for current sources, if they are in, they can't be, we don't connect voltage sources in parallel. We don't connect current sources in series this way, but we can, if you want to connect voltage sources, we connect them in series, as you see here. If you want to connect current sources, we connect them in parallel. So when you connect them in parallel, if they are in the same direction, as you see here, both of them in the same direction, you can just add the current. Okay? Same thing, if you change the direction here, still you can add the current, but it has to be this way. But if they have different direction, so in this case we are gonna subtract. Okay. So here, if I take the direction of this one up, so it has to be IA minus IB. I can say also, I can do it like, I can take this direction here, but in this case, it is IB minus IA. Okay, guys. Again, what I want to say here is sometimes, sometimes that's what I'm explaining here. Sometimes you may have a circuit like this one. You have some sources are connected this way. So in this case, I can replace. So as you see here, if you have two voltage sources connected in series, regardless how they are connected, in this case, because I connect the negative to positive, so that means I'm gonna add. So here I can make it only one source. Same thing, if you have current sources that are in parallel, I can replace it with only one source. Either if they are the same direction, I can add different direction, I can subtract. Okay. Any questions? Okay. I think this is the end of chapter 3. Let me what tell you. I want to link chapter 3 to chapter 4. Okay. Chapter 3, guys, is about analysis of resistive circuits. Okay. I told you before, if I want to analyze a circuit, what it means? It means I want to find the voltage and the current everywhere in the circuit, in every branch. That's the meaning of it. Okay. By the way, in chapter 3, we have already did that. So why do we have new chapter here about the same topic? That's what I'm going to explain now. So here, if I go to chapter 3, I just want to make a link. So if I go to here, the example, so here, in this example, for example, here, if you look at this example, I give you this circuit, okay? And then I use Kirchhoff law. I used here Kirchhoff current law, Kirchhoff voltage law, and also Ohm's law. I used them to calculate the current and voltage everywhere. So we already did it. You understand what I'm saying? Okay. So as you see here, in this example, we already did it here. Okay. So why we are going to do the same topic again? The reason is this is one approach. And I'm going to repeat it in chapter 4. So I'm going to repeat this approach, the same thing here. I'm going to repeat it in chapter 4 because this is one way to do analysis. However, sometimes we're always looking for a less complex way or an efficient way to do analysis. So what I'm going to do in chapter 4, I'm going to explain 3 different approaches to do analysis. One of the approaches is what I have already explained in chapter 3. Okay? So this is one approach. I'm going to explain two other approaches. Okay? The 3 approaches are doing the same thing. But maybe in some circuits, one approach is going to be more efficient or easier than the other approaches. You got what I'm saying? That's how it is. Okay? We always look for an approach that has fewer number of equations. So we need to reduce the complexity of the circuit. For sure, this is a very small circuit. In reality, if this is a big circuit, it's gonna become too complex. Okay. So again, this is the way I can link chapter 3 to 4. So chapter 4. Here, I'm gonna explain here in this chapter. We need to do analysis for resistive circuit. Analysis means I want to find the current, the voltage everywhere in the circuit. To do that, we have 3 approaches. The first approach, we call it branch current method. And this is the same approach I used in chapter 3. Okay? And then I'm going to explain two more approaches, which sometimes these 2 approaches are more efficient than this one. It's easier than this one. In some circuits, maybe this one is easier. In some circuits, this one is easier. You got what I'm saying? So anyway, so the 3 approaches are exactly doing the same thing, but in different ways. So let's start with the first one. And the first one, again, nothing is new. It's exactly the same thing I explained in chapter 3. Okay? So here, let's start with the first one here. So the first one here, the first method here is actually this method, branch current method. In this method, we are using Kirchhoff current law, Kirchhoff voltage law, and Ohm's law. Okay? In the other 2 approaches here, we use Ohm's law and one of these 2. So you will find here in the first approach, we use current law and voltage law, Kirchhoff and Ohm's law. But the other 2 approaches, in one approach, I'm going to use Ohm's law with the Kirchhoff voltage law only. In the other approach, I'm going to use Ohm's with only current. Okay? But anyway, let's focus on the first one. The first one here, again, nothing is new. It's a branch current method. So you will see, I give you the steps. Again, similar to what I did before. Here, if I give you a circuit like this one, you need to find here, I give you this circuit here. So in this approach, this approach is called the branch current method, because, look here, guys, if here I'm assuming current, there is a current coming this way, I'm going to call it I1. And there is a current coming this way, I'm going to call it I2. And there is a current coming this way, I'm going to call it I3. Is that okay? Let me ask you a question. If I find a way to calculate I1, I2, I3, is that enough? Yeah, you can easily calculate the voltages. I solve it everything. If I just can get I1, I2, and I3, it's very easy to calculate the voltage drop using Ohm's law. It's very easy to put the voltage drop using Ohm's law. Same thing here. So that's why this approach here, I'm gonna focus on creating equations that has these 3 unknowns and solve the equation to get the 3 currents. Once you have the current, you can get the voltage everywhere. This is the main thing. Okay. So again, that's exactly what I did in chapter 3. I will try to use Kirchhoff. I need, because I have 3 unknowns here, so at least I need 3 equations. I need 3 equations in 3 unknowns, I1, I2, I3. Solve this equation, get I1, 2, 3. Once I get I1, 2, 3, I'm done. You can easily calculate using Ohm's law, you can easily calculate the voltage. Okay. First of all, let's do, for example, here, the first one here, current. So now I want, again, I need to get 3 equations for I1, I2, I3. That's what and then I solve them. There is a very easy way now to get one equation, Kirchhoff current law. So in Kirchhoff current law, this current here, I can take this node, and you can see I1 is equal to I2 plus I3. The current input to a node equal to the current output of a node. This is the first equation. So now I get 1 equation. I have 3 unknowns. I need to get 2 more equations. You got it? So the first equation, I can get it from Kirchhoff current law. I can apply here at this point. Input current I1, output current I2, and then output current is I3. This is 1 equation. I still need 2. Yeah, very easy. I can apply Kirchhoff voltage law here in this loop. This will give me 1 equation. I apply here Kirchhoff voltage law here to give me another equation. After that, okay, I'm done. I can have 3 equations. So let's apply as again. I'm not explaining anything new. That's exactly what I did in chapter 3. But I just want to link between what I did in chapter 3 and the 2 other approaches that sometimes they are more efficient or easier than this approach. Okay. So here, I'm going to take this loop here. Okay. And then summation, this is the voltage law. Summation of the voltage is equal to 0. So what is here? I'm going to assume this is the positive direction. So any current in this direction, I'm going to take it positive. Anything that's opposite to this direction, negative. Okay. So here, this is the positive direction. So here is the voltage here plus the voltage here plus the voltage here equal to 0. This is Kirchhoff voltage law. Okay. Now look at the direct. So here I have 1 voltage plus 1 voltage plus 1 voltage equal to 0. Now look at the sign. Which one is positive? Which one is negative? Okay. Very easy. Now this is the positive direction and the current is this way. So this voltage here has to be positive. Here I assume the current is this way and also the positive direction is this way. So this is positive. And now because this one is encountering the negative first, so this one will be negative. Okay, let's do it. So now what is the voltage drop here? Very easy. I1 times R1. Yeah, I1 times R1. What is the positive? Because the direction here is similar to the direction here. Okay. You can assume any direction, but I think just let's to make it easy for us in grading, you can make any direction. But let's be consistent in this course. Always let's make the direction clockwise. So here you can see this clockwise and this clockwise. Okay. So here, if you do make it clockwise, that's okay, as long as the result is correct. But because it can be easier just in calculation in grading. So anyway, so here, what is the voltage drop here? I2 times R2 positive, as you see here, and this one is negative. This one is come here, it is negative. Okay, so this is a second formula, second equation that between I give you R1, I give you R2, I give you VS1. Okay, so in this case, I can get a second equation between I1 and I2. So I need one more equation, okay, because I have 3 variables. Same thing, I'm going to do it again here. We have a drop here. This drop is actually I3 times R3. We have a drop here, which I2 times R2. We have a drop here, which is VS2. Summation is equal to 0. But now look at the sign. Which one is positive, which one is negative? Okay, very easy. Now this is direction here. The direction here is similar to the current here. So this one has to be positive. I3 positive. Okay. Because this direction here is going to encounter the positive first, so it has to be positive. Okay. Look at this one. The current is this way. I assume it is this way. So this one is going to be different in different direction. So this one, the current this way, but this one, so that's why this one should be negative. Okay. Anyway, you just plug in, you get by this way. Again, I apply Kirchhoff current law here, got one equation. I apply Kirchhoff voltage law here, I got one equation. I apply Kirchhoff voltage law here to get answer. By the way, guys, please, if you don't understand Kirchhoff current law, Kirchhoff voltage law, I'm sorry, you can't continue this course because I'm going to use it at Ohm's law. These 3 laws, I'm going to use it until the end of the semester. Okay, so they are going to use it all the time. Okay, so you need to understand them very well. Anyway, so now I have 3 equations. I can solve the 3 equations as I told you before. Any exams in anything, you need to, I can make it like a matrix this way as I told you before. You should have a calculator to calculate the inverse of this matrix and then get the current here. Okay. Once I have the current, so here I have I1, I2, I3, I am done. I can simply calculate V1. V1 is actually I1 times R1. I can calculate V3, which is I3 times R3. I can calculate V2, I2 times R2, and that's what I did here. Okay. And the current here is the same like the current here. So the current here, because they are series. Okay. Also, the current here will be the same like the current here. Okay. But here, usually the current here from negative to positive for batteries. But actually the current here is going to be from positive to negative. So that's why you can see negative sign here. Okay. but here is gonna be positive because it's gonna be true negative. Anyway, so again, I just Ohm's law, I multiply I by R to get the. That's it. Any question, guys? Again, let me summarize to in this lecture to start the quiz. Very simple. So in this chapter, I'm explaining 3 approaches to analyze circuits. Okay, one approach I have already explained from chapter 3, and this approach is using Ohm's law, Kirchhoff's voltage law, Kirchhoff's current law. Okay, all of them have the same idea. All of them. The 3 approaches here, we create equations for unknowns and solve the equations. Okay, but some of them I'm going to create equations for current. Some of them I'm going to create equations for voltages. But I have some unknowns. You create equations, solve the equation. Once you get the part of the voltage, you can calculate it between counters. Okay. So again, I here nothing is new. It's similar to what I explained before. Next time I'm going to explain these 2 approaches, which sometimes they are easier than this approach. Okay. Anyway, that's enough. Thanks.